is now being recorded.
Okay. So good morning everyone and welcome to the ICT webinar organized by EeB-CA2 CSA. So just to remind you quickly what EeB-CA2 CSA consists in, it's one of the 4 CSAs dealing with energy efficient buildings, also with almanac, e-birth and swimming, which are more focused on some specific issues. And EeB-CA2 is the umbrella CSA, and our activities include some different things such as clustering workshops to help establish synergies among the EeB-PPP projects. We also offer dissemination opportunities in international sales. We also propose some trainings and webinars such as the one today on research and development, technology transfer and exploitation. And also we have a set of online tools and services to enhance visibility of projects. So the agenda today, we will have a presentation of Shrimp Forest Technologies by Alberto and Mark. Mr. Speccatori finally couldn't join. And then we will have an exchange with the audience, so this will be a question and answer time, and I will moderate it. And also a short conclusion by my colleagues from EeB-CA2 about the services we propose. So during the webinar, I kindly ask all the participants to mute your phone to avoid disturbing noises. And regarding the Q&A session, I will be the moderator, so if you have any comment or question, just click on the raise your hand button and I will give you the floor. And we will also share the PowerPoint presentations after the webinar. Yeah. So, Alberto, I give you the floor.
Yes. Yep.
So this is the first presentation.
Yep.
And you can switch the slides by yourself.
Okay. So thank you very much, and sorry, I'd like to start from the beginning. Okay. Welcome to this webinar. This webinar is about the SimForUs project and the results and the technology that we developed during this last FP7 project. The index is very simple. We simply introduce the SimForUs project very shortly. Then Mark will tell you about the system architecture. And then unfortunately I have to come back again because the third presenter is going to be father now and and cannot be present, and I apologize, Massimo Baccarini. So what about SimForUs project? It was a project headed by Cofeli, GDF Suez company, Cofeli Italy. And I already introduced it by phone just without any support for the images. And you can see the partner on the right. And here is the Barcelona metro station. And the energy consumption of the Barcelona metro station, the slide about the energy consumption. And I was just jumping to this slide where I was talking about the pilot, the metro station, where the pilot was a Passage de Gracia pilot, was quite an old station, which 35 passengers per year, so very busy station. And we were just jumped here when I show here the third block of the station, and on the right side the CAD model of the station, and we control the upper part of the station, which is line 3 station. The station, the Passage de Gracia, has a very standard ventilation system. So I'm going to introduce the system that we controlled. The ventilation system was made by 2 tunnel fans and 2 station fans that are managed according to a predetermined workflow. This is a standard ventilation design for underground stations. The tunnel fan operates daily according to a predefined schedule. What that means is that during the day, the tunnel fan, the one that you see here, extract area exhausted from the tunnels while the station fan inflates fresh air into the station and then into the tunnels. During the night, the main purpose is to refresh the tunnel. So the tunnel fan, the station fan are switched off, and the tunnel fan inflate area into the tunnels in order to refresh the tunnels. Because during the night we don't have traveling trains. Lighting was very old T8 fluorescent technology that are switched on and off according to the working period of the station, the opening timing of the station. Finally, passenger transfer are operated by standard escalator and lift systems. So this were the situation that we found. And the question is now that the pollutant levels depend heavily on the ventilation system. So due to the ventilation system, here you can find an animation to see what happens to the pollutants when the train comes in the red one after PM days particle density. So we simulated all this stuff before operating into the system. So this means that we have to control either energy, but also the comfort, which means temperature and the pollutant levels within the station. Why do we need to control the station? Here you can see three complex graphs. On the left side, you see the station. The two tunnel fans are marked as blue and orange arrow. So during the night, tunnel fans inflate, and there should be airflow entering the station from both sides of the station. But there are dynamics that are not foreseen of the original design of the ventilation system, and one depends from the fact that the nearby station on the line 3, diagonal Passeggio di Grazia in Catalonia, we are controlling the middle one, Passeggio di Grazia, are on a slope. So since the tunnel are very hot, the metro line behaves like a big simile and have a strong buoyancy problem. What this causes is that, as you can see, the three orange arrows are 3 nights, subsequent nights during August, and as you can see, the graph are the inflow rate of the two stations. That orange tunnel fan 2, actually the inflow is almost zero, so it doesn't operate during the night here, and here. While the blue one is favored by the buoyancy effect, so it is able to operate into the night of 25th of August, 26th of August, but during the night of 27th of August, since winds from the northwest rise at a certain speed, and you can see it on the middle graph, the orange, this orange arrow on the middle graph, where you see direction and speed of this wind. Well, this wind behaves like closing the door of the station, so even the blue tunnel fan 1 stops operating or blowing inside the station. So despite the one we are running, there was not inflow into the station, which means that energy is fasted, that the forcing behavior is not actuated, and thus that we need dynamic control. So intelligent control that takes care of all these very, very complex dynamics. This was the reason why we developed these technologies. Here you can see finally for the energy audit of the station, the three systems that we are going to control encompass 61% of the energy consumed by the station. The other 20% are vending machines, television, photo robots, something that can just switch on and off, and that were just due to poor management, their consumption. So we didn't control it because it was very easy. I didn't put any far advance into the technology. And the final 19% was out of scope for our project because it was waterfall conception and other aspects. As a total, we controlled 24/7 in lighting, 74 megawatt hour per year for ventilation, and 37 for the escalator. So this is the energy audit. The approach we did was twofold. We have two kinds of aspects to control. One was the environmental control, so energy due to ventilation and comfort. and this requires a model predictive control because we have a dynamic that depends on the state of the system. So energy depends on the state accumulated by the walls, and so the history of the energy dynamics matters in control. And we have to implement model predictive control. On the other side, with the other two systems, reactive lighting control and reactive passenger transfer control, we were able to just use a very simplified control, which depends basically on occupancy detection. Saving rate we achieved at a project was considerable, or at least this was the judgment of our reviewers, was 24 for lighting, 35%, these are measured, so the uncertainty into the measurement, 35 for ventilation, 88.5 for the passenger transfer. So quite reasonable, quite good saving rate, which in a sense it translated into gigawatt hour per year projected into the whole metal network of Barcelona give you this very huge figure of energy saving and energy saving potentials. As a financial sustainability of the whole technology, this is the overview of the system. Then we will go into the technical detail with the other two presentations. As a financial sustainability, with some optimization, we can come to 5.5 years of payback with this measured saving rates. I mean, this is quite good for an energy saving measure. Okay, so at the end we were able to control the systems of a station in a very energy efficient way. If we want to move up, what are the scenarios that we can we can face? Well, extending this control to a wood metal line, we will project ourselves into a scenario of intelligent agent systems that cooperate in order to control a metal network. And this will be a very big advance because we don't know, to our knowledge, worldwide that there are systems developed to this level. And it would be a pity if we won't be able to do this further step. Lesson learned, intelligent management system is a valuable complement to standard passive energy efficient solution. They are enabling technology for integration of buildings into smart city context and can provide marketing challenges. As a final slide, I want to give you some references. I don't know whether you can see them, but you can download the slide and we published up to 10 journal papers with this about these results. So I have wrapped up the very first idea to what matters about the project. I mean, what is the project focus? And then I give the floor to Mark to give you more detail about the hardware and the system level, the system architecture, and then I will be back to give further details about the control technology. So thank you, and over to Mark.
Okay, so shall I also then share my screen, or shall we do the role of the technical management? And we were also heavily involved in many of the software components. The hardware development was done by VTT Finland, but I am going to present details about hardware as well as software details. So about the software architecture or the system architecture, we had, of course, a lot of different devices to integrate. I think this way, yeah, there should be a pointer now. There were, first of all, many sensors, of course. Then we had to integrate the CCTV, the surveillance cameras for occupancy detection. We also used external data from a weather forecasting service. And then we had actuators for controlling the lights, fans, and escalators. So the first task and the first challenge was to integrate all these devices. And of course, as you can imagine, They were quite heterogeneous in terms of protocols, and for this we used the LinkSmart middleware. This is a middleware that was developed by Fraunhofer, and the idea of LinkSmart is to provide proxies for each device, and a proxy, you can see it as a driver on a higher level. So a proxy talks to the actual device and provides a REST interface to higher level components which then access these devices. Okay, so from there on, data was then sent to components we called monitoring. These were actually more, I would call them post-processing components, which gave semantics to the actual raw data. So, for instance, you had raw data coming from a PM10 sensor or from anemometers, and what you actually wanted to know about was the airflow. So these components took several sensor data and gave them a better meaning in terms of what does it mean in terms of airflow. From there, the data went into models and the controlling component, and based on the defined policies, the control, again, over the LinkSmart proxies, controlled the devices over the actuators. Then we had graphical and textual user interfaces for being able to monitor the actual data and to see what the system is working on. And we had some assistant components, for instance, a supervision component that was supervising and monitoring that all the other components were working, and that we had alerts when one of the components or several ones were failing. And of course databases, because all the data that was generated was stored to the database, and historical data was also used for the control policies later on. So getting into some details about these systems, the backbone. So this was the list of all the the different kinds of sensors we had. The idea was to provide a low power sensor network, because the sensors were battery powered, and we wanted the sensors and the batteries to last as long as possible. We had a reliable communication framework for that, and so it was based on RS482 wired serial industry standard, and it was developed in a fault-tolerant architecture. And here you can see some of the sensors as examples. For the occupancy detection, we got access to the surveillance cameras that were placed or that were already in place. For that, we installed a hardware that gave us access to the camera streams, and we could run our system in parallel. The idea was to detect an occupancy, not exactly how many people were in a particular place, but we divided it into 5 levels, so our system was able to detect if there are very few people, medium people, or many people, and in 5 different levels. The idea was that you get the camera image from the CCTV cameras, and you have one image of the same location where no person is at that time, and then you do actually a subtraction, and what you get is just the people. And from that, it was possible to run image recognition algorithms on it and to detect this occupancy. The good thing about that is that you don't have any privacy issues because you actually operate only on these kind of pictures. So the actual pictures with people on it were dropped immediately after this subtraction step, and it provided a good enough estimation in really real time. And it could run also in parallel to the actual surveillance camera because we had this this capture of the camera stream, but the second stream was then streamed to the surveillance team as it was before we started with the project. For the ventilation, so before we started, the fans were controlled by a system of TMB. So TMB is, by the way, the metro provider in Barcelona. The system is called CSA, and before CSA told the fan frequency variator in which speed the fan should run. And now we wanted to set the actual speed from our SeamForUs system, and for that we installed another PLC, a backup PLC, which was also able to control the fan frequency variator, and the backup PLC then got the signals from our server. We also installed another hardware, a switching logic, which decided which signals should be used by the fan frequency variator, either the CSA signals or the SeamForUs signals. It was said in a way that if the switching logic didn't recognize or didn't get any signal from SeamForUs, then it took CSA. So that it was made sure that if SeamForUs is down or not working for some reason, then the normal default mode by CSA was set. And I mean, this was a mode that was tested for several years. Also, it was possible to manually switch back to CSA. So in case you, as a system operator of TMB, you feel, okay, it's much too hot and you see the fans are off, so obviously SeamForUs is not working, you were able to manually switch it off. And for that, we modified a cabinet in the control room and added manual switches from which you could control the switching logic to switch between CSA and SeamForUs. And here, this is a picture of the backup PLC which we used, and here you see it integrated in the cabinet. For the light control, so first of all, we replaced the old T8 lights by more efficient T5 lights, and we used lights that were controllable. So the light level, the actual light level was controllable. That was not possible with the old T8 lights. And now it was controllable over a standard protocol for lights, and that is called DALI. It seems to be a standard protocol for lights in general. We had a company from Barcelona which developed these T5 lights, and they provided us such a gateway that was programmable for our system. So our signals came from the server to this DALI gateway, and the DALI gateway controlled then the actual lighting. And finally, for the escalator control, the escalators installed in the station, they are from Thyssen, and TMB planned anyways to install radars. These radars to detect if somebody is going to enter the escalator or not. We used the possibility that Thyssen had to come anyways to install the radars to also modify the existing frequency drive for Thyssen, and the escalator control that is now actually working as the switching logic is working for the fans, meaning that it can switch between the SysIF, the former system, and our system that was again controlled over a back-off PLC. The frequency variator was modified in a way that you could now switch between high speed or full speed and a lower speed. That's what we wanted. Alberto, you are going to tell later about the control policies, right?
Mm-hmm. Yes.
Yeah. Okay. Then coming to the Link Smart middleware, oh, actually there's an image missing, but doesn't matter. The idea of Link Smart is, as I said, you have device connectors, is what we call them, and they provide a means of communicating to the actual devices and then providing access to these devices over REST interfaces. And then you build a Link Smart network out of it. So all the devices which are connected over a device connector then are in a Link Smart network, and applications and services can access them over these network and over the device connectors. Over this process of Link Smart enabling them over device connector, it is made sure that all the devices are pushed to a resource catalog, and if they have services, also these services are pushed to a service catalog so that all the applications and services can detect it and discover it over these catalogs. And finally, there's MQTT-based message broker provided, over which publish, subscribe data exchange works. There's the picture. Okay, now here you see the picture. So IoT devices talking over their proprietary protocols to the Link Smart device connectors, and the Link Smart device connectors are then providing high-level protocols to applications. Okay, and finally, maybe. Well, that's actually not the slide that I provided. This is the one. Okay. So this was the user interface. Finally, we had here you see the station again, an overview of the station where all the sensors are. Here you see the live values automatically updated, filtered by device levels or device kinds, and here is some post-processed data. That's what I told before. For instance, the actual PM10 sensors, they measure number of particles, but what you actually want to know is the PM10 concentration, and something that was calculated like this is seen here in this area. And finally, you had the weather forecast from an external weather forecasting service as additional information. Okay, this was it from my side. Then I would hand back over to Alberto.
Okay. How can I proceed on just through this screen, or I can share my screen? Start sharing my screen again. Okay. It seems it works this time. Tell me if you can see. Can you see my screen?
Not yet, but yes, now it's fine.
Okay, it works.
Yes.
Mm-hmm. Okay, so just so this is about. To speak very quickly, I will run through the control logics, which are the upper module that sits just on top of the Link Smart layer. The first module takes the data from the Link Smart to Link Smart protocols and do a lot of post-processing because data are usually dirty. So we have to low-pass do filtering, so low-pass filtering, do some resampling in order to get that in the real timeline, so everything can be synchronized. This means there is the meaning of resampling. And then we apply some post-processing function. One of them is very important, and we added to the data, the single data, the reliability, which means how an estimation of whether the sensor is working or good or badly, so that then we can write a signal to the upper module to say that we are not working properly. This was a sort of safety measure that was explicitly asked by our partner TMB, which is the network manager, and have to grant for safety of their people, so of the passenger or conductors. So they require us to work in a sort of robust way. Okay, moving on. We control three systems. The first one is the ventilation. The most complex one is the ventilation. So ventilation, it depends on the data that works about ventilation is occupancy, so how many people are there, and PM10 concentration, CO2 concentration, the air temperature that altogether make the comfort level of the system, so the state. Disturbances are wind direction and high speed in general into the tunnel due to the piston effect of the trains. And what we control are the fan here, the fan speed. The control, the general idea of the control system, this is a model predictive control. So the external data comes into the model predictive control and feeds the model that gives prediction to the controller. And the controller makes the best estimation of what is the actuator funds that satisfy a control policy that I'm going to tell you about in a few seconds, and then control the actuator funds for the station. The first thing that is very interesting to talk about is the model that do the prediction of what may happen if I am in this condition and I change the fan speed in a certain way. And this has been implemented as a Bayesian model. So there is a Bayesian network driving the fan station, which do the prediction of what may happen. A Bayesian model that takes all the data from the incoming data and do the control data outside, do the estimation of what may happen. So the next stage and what that may happen if I turn the fan to a certain speed instead of another one, and so on and so forth. Bayesian network is very important because it's a statistical model and it can self-learn from data. So what you see, the structure of the Bayesian network has been self-learned by data measured during the first training period. As you see, the power of the system here, the exchange estimation, the pollutants estimation, and the temperature estimation. Here is the control policy and the general controller. So what we have seen, just the model that makes the prediction, but then once the prediction has been done, there is a controller that has to select the best setup for the fan speed. And the controller minimizes a function that is quite complex here to discuss, but basically, as you can see here, can have many components, weighted components, and components are power, temperature, air exchange, CO2 level, PM10 levels, and another component which is for the stability, technical stability of the sun. There are all the fans. So these are weighted components, and if you change the weights here, you can select different control policy, one that maximizes energy savings instead of comfort, or a balance between the two. There are constraints that we have to impose in order to grant for the reliability of the system, and in terms of what are the minimum air exchange allowed, the minimum CO2 allowed, and so on and so forth. So how the controller works, this is the flow chart. There is an outer loop that is just activated every 10 minutes. So every 10 minutes there is the control policy is activated, and the control policies get the data, generate a candidate control policy. One of them instantiates environmental predictor with post-process data, so make prediction of what happens to the model, and then calculate the value of the control policy, the cost function, and do this many times as much as possible in order to generate many candidates, and then select the best one. This is done every 10 minutes, and the running time is very fast. So there are plenty of room to improve and to go, because the Bayesian network model is very effective in that. I will skip these two slides, and these are an example of a control policy. So what happens on Friday, in October, and weekly, a weekday and a holiday day, and Sunday. So these are measured data occupancy, and these are active power and fan frequency controlled. The blue line are the constraints that the system has to, and as you can see, they are within the constraints in both situations. And on Sunday, we have the possibility of really run very low in power, because due on different environmental conditions. And this is something that can be estimated every 10 minutes by the system running. Going to the lighting policy very quickly, the light policy is reactive, so it depends on the occupancy or the passenger occupancy level in the platform that they are calculated or measured by the system that Mark introduced you. And the idea is very simple. It's just the reverse of the intuition. The more people are in the platform, the lower is the lighting level, because it is dependent on the visual task. When you are in a rush hour, you don't need to look very far away, because you have people very close to you, so you don't need many lights, and you feel secure, you feel safe. If you are alone at 10 p.m. in a metro station and someone is approaching you, you need to you want to see the face from far away, and you need really more light. So the lighting control policy depends on occupancy, and this is our occupancy level in our station. And the more people are there, and the less light is put on, of course, within the constraints of the regulations. And what we see here is a graph of controlling. The blue line is switch on and off, is what was the previous policy, and now the orange one and the red are what you can save with this modulation of lighting. And as I say, we can go to 24%, about 24%. This final graph is about the lighting level with respect to the occupancy, calculated occupancy. As you can see, higher occupancy, lower level, and vice versa. Finally, lighting saving. There are two rooms we have controlled, and we saved 15 and 28 on the average, 24% from both. Finally, the escalator. The escalator is the most tricky one. It has a lot of optimization due to the fact that the escalation can start and stop by their own. We modeled the escalator, and we just used our knowledge about how many people are in the station to switch on and off the escalator at different speeds, so 0.5 meters per second and 0.4 meters per second, depending on the level of occupancy of the platform, so that you cannot engage people queuing into waiting for the escalator. So many people in the station go to uppermost level speed, and low people lower speed. And as Mark said, we put further sensors, and this is the occupancy of the platform and the threshold on the control, the threshold and the control logic that we implemented. So 0.5 up over the threshold of 15 people per person into the station, and lower speed on the other side. Again, this is the occupancy had a hint how much we control in the way we control the escalator. So upper and lower hint, upper speed and lower speed depending on occupancy, and the saving is 8.5. It's not very much actually, but it's the most we can get out of this device. So we run very quickly because there was a lot to say, to tell you. And we are more or less in time. And this concludes our presentation, and we are open to questions.
Okay, thank you very much, Alberto and Mark, for this very complete presentation. So we will now go on with the question and answer session. So if anyone has a comment or a question, just wave your hand. Yes, Francisca.
Okay, hello, this is Francisca. I just would like to know, what are your next steps?
Sorry, your volume is very low, Francisca. Can you?
I would like to know which are your next steps with this technology.
Next step with this technology. Well, at the moment, what we did now is we have done a big experiment and a big demonstrator, very expensive for the result, of course. But we know all what matters in order to control a metro station in an efficient way with reasonable payback period. The next step is to we have to basically move to this. We are about between 6 and 7, if I well understood the development level, technology development level, and we have to move up into the industrialization. So we have to do is twofold. On one side, we have to reduce the system to its minimum. We already know how to do this, but we have not investment to do this. So in other words, we have to produce a system that is a very low impact into the metro management, metro maintenance organization, and which costs no more than 20,000 euro per installation, which is really challenging, but we are very close to this understanding. So we need some investment to do that. And the second step is to develop a further layer, which is a sort of multi-agent layer, which allows this single station controller to communicate and negotiate energy power and energy policy with other nearby stations at the internal farm, and possibly with the upper overground level of the smart city environment. One of the real challenges we would like to face are demand response. In terms of, at present, this station is able to include in its control policy straightforwardly the cost of the quality of the energy supplied by the energy supplier, whether the energy is produced by renewable and which may be included into the cost, per meter, or as a separate information, to configure the station accordingly. So this is all a lot of things that are straightforward for us, and we have to find a call to do this further step, or private investment that want to further develop this system to make money with that.
Okay, thank you.
Okay, thank you very much for your answer, and good luck on that.
Yeah, thank you.
Is there any other question or comment? No. Okay. Then I will give the floor to Francisca again for a short conclusion and presentation of the services offered by EeB-CA2.
Yes, thank you. And thank you, Alberto and Mark, for your very interesting presentation. I'm now just providing you a brief few more information about the upcoming activities that we are implementing and offering to you within the EeB-CA2 CSA. On the one hand, you have the opportunity to promote your project in a booth at the ECTP conference, which will take place on 17th and 18th of November in Brussels. If you are interested in that, you can contact Anne-Claire. Also, just click on the link that you see on the button of the slide. During the ECTP conference, we will also organize an energy efficient buildings matchmaking event. If you would like to register and upload a profile, you can also click on the link below. This is free of charge, so you don't need to actually participate in the ECTP conference in order to participate in the matchmaking. And it is a very good way to meet new cooperation partners in order to, for example, start new cooperations in terms of new research projects, businesses, or if you're even looking for investors, you also have a chance to meet them there. So if you would like to participate, just click on the link below and upload a meaningful profile. And until the end of January, you also have the chance to participate in our coaching services, which we are calling Innovation Assessment. The Innovation Assessment is an analysis of your innovation strategy in order to analyze together with one project partner of each of the projects their innovation potential in terms of their newly developed technologies in one of the EEB projects. So what we do is that we analyze your competitive potential, your innovation potential, and give you some feedback on our findings. If you would like to have this benefit from this free service, you can contact me. If you haven't done so, please feel free to join our LinkedIn group, the ECTP Energy Efficient Buildings Committee LinkedIn group. It is a community with more than 700 members now, and is a good way for you to publish your deliverables, newsletters, upcoming events, or also start technical discussions. Also, lots of the other members are already using it actively, so it is a good way to stay informed about events and further ongoing activities in the community.
Okay. Thank you, Franziska. And I also take this opportunity to remind you that next Monday, so on the 7th of November, from 12 to 1 p.m., we will have the last EeB-CA2 webinar dealing with BIM issues with the presentation of 5G technologies. So if you wish to attend the webinar, just send me an email and I will send you back the invitation and the information. Okay, so thank you again, Alberto and Mark, for your cooperation.
Okay.
Thank you, everyone, and I wish you a nice weekend.
Okay.
Thank you
all. Bye-bye.
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 Bye-bye.